receivers out there, notably the awesome one developed by Stanford back in 2010, and another by the Wuhan group, which are deployed in various locations, some in Antarctica. But we wanted to update specifically the awesome design and make it a little more modern. I'll preface with why we should study the ionosphere. Many satellites orbit past it, many forms of communication pass through the ionosphere, whether it's radio or other forms. Space weather can affect ionospheric density because it is a plasma, and specifically from space weather affecting it, you can see electron precipitation down from the radiation belts. Those interact with ions and can lead to ozone depletion and various other phenomena. And so where do very low frequency waves come in all of this? Well, plasma number, the plasma density, allows the ionosphere to reflect VLF waves, and specifically the D region of the ionosphere, which is the lowest part of it. And since it's able to reflect it, VLF waves also reflect off of the Earth's surface, so they're able to propagate in the Earth ionosphere waveguide. And this just comes from transmitters. We use several Navy transmitters. There's a couple in the US, one in Arlington, one in South Dakota, and we're making use of those in this project. And we can see changes in the ionospheric density by an amplitude shift in these VLF waves that we're detecting. We had a couple goals for the differences from Awesome's design to Avid's design. The main one was to simplify the design with a focus on timing. Another was to modernize component choices. And with that, we also wanted to make our own power board and use off-the-shelf boards for simplicity where we could. So I'll go into a brief mechanical systems overview. The preamp really hasn't changed that much from our system to the Avid system, the Awesome system to the Avid system. And that consists of the actual receiver antennas and the preamp box. That design has remained mostly unchanged. The real changes come when we get to the line receiver. As you'll see with the Awesome system, it was a line receiver box and then external GPS storage computer and data acquisitions card. And we've managed to condense that all into one enclosure that fits on the server rack. So going over some of those line receiver changes, the first one, we made our own power board. We're starting with 19 volts just from a computer power supply, and we're able to get plus and minus 15 volts, plus and minus 5 volts, and plus 3.3 volts. This is just a National Instruments data acquisitions card that we use for most of the data processing, and we just buy that off the shelf. And we're also using a single board computer with Windows installed on it, which makes it a little bit easier to interface. And so moving on to our main goal, which was to simplify timing, we had to modify the motherboard a little bit. Originally, we used an FPGA and crystal oscillator to control our timing. And it was shown by this nasty circuit you see up there. We were able to replace that with a GPS discipline oscillator that we just bought off the shelf from Synergy Systems, and this made the design a whole lot easier and also more accurate. And so I'll move into the meat and potatoes of this talk, which is the filter card and the preamp card. We had a unique opportunity because we were making so many of these systems to really get an in-depth look at the frequency response analyses of each card and compare that across the board. The filter card is relatively simple. It's just a 3 Hz low pass filter and a 46.9 kilohertz low pass filter. Sorry, 3.3 Hz high pass filter. And we have a 12th order Butterworth filter, which is a little unusual. Usually people use 8th order. We're using 12th order because we really need a sharp cutoff at 46.9 kilohertz. It's for a couple reasons. 46.9 kilohertz is really close to our Nyquist frequency, so if we go above 50 kilohertz, we start getting aliasing with our signal. And there's also a transmitter in Hawaii, which transmits at 40.9 kilohertz. This in our frequency response analyses for the filter cards. You'll notice that really sharp decline at 46.9 kilohertz, which is exactly what we want. And across the spectrum that we care about, which is 3 to 30 kilohertz for most VLF transmissions, we're seeing less than 2 sigma deviation from the mean in all 30 of our filter cards, which is really good for us. Then we can move on to the preamp cards. This is a little more complicated. We had to start with hand winding our own transformers that we made in-house because no one makes a 24 to 548 winding ratio. And that immediately goes into a bipolar junction transistor circuit. We're using BJTs here because we want 50 decibels of gain. Op amps won't give us that without a significant amount of saturation, and then we get a lot of noise in our system. And that's just followed with a non-inverting op amp, a 2 hertz high pass filter, and an integrator, which gives us a nice sine wave output. What we can add to this base circuit, first thing we can add is a 9 kHz cutoff. We don't usually use this, but if we are in a really noisy area of deployment, we can adjust for this option and cut off those really low frequency signals that we don't want. We can also adjust the gain. We usually function at 0 decibels, but we can raise it to 10, 20, or 30 decibels. This is if our signal is really low and we can't just compare it with the noise. We can also use a PIC microcontroller to inject a calibration signal at the start of the system, and that allows us to calibrate in the field. And looking at the preamp FRAs, the response is really similar across the board. You'll notice on the 0 dB mode, we have a hump. We're able to circumnavigate this for a couple reasons. First, the hump doesn't really increase until after the frequencies that we care about. And the second is that we're doing in-field calibration with the system, so we know the base response of the system. And if you're looking at the 30 dB and noticing it falling off really quickly, that's just op-amp saturation. So speaking a little on that cone calibration that we're using the PIC microcontroller, and that's injecting a cone signal at the start of the preamp card, which runs all the way through to our computer, and then we can output it. And we're using a signal that's peaking in power every 250 hertz across a 0 to 50 kilohertz range. And this gives us a nice output, which allows for the full calibration of the system. And we can see that here. And so you'll notice right away that the shapes are very similar. You'll also notice on the bottom, which is our preamp card FRA with a filter card FRA, that the points are not distributed like they are for the cone calibration. That's because for the FRAs, we're sampling 30 times per decade, and the cone calibration is 250 hertz. Slight differences in decibel range, that might just be for a variety of reasons. We have a couple ideas, but we haven't been able to test that in-house yet. And using the system, we were able to get some initial data on the solar flare back in December. The signals were starting at the Arlington VLF transmitter and went across to central Canada up there in Gillilam Island Lake and Pinellas stations. And we see this really nice display of the receivers detecting the change in atmospheric density as the solar flare hit with that peak around 2200 hours. So the data is really promising, and we're excited to get working with it a lot more. Just to remind you of our goals, we're to simplify the design with the focus on timing, which we did. We modernized the components, and because we were building over 60 cards for this project, we found that response shapes were similar across all the FRAs and calibration that we've done. And if you're interested, on the diagram on the right, that is the array for VLF imaging of the E region. We have deployed 9 such sites. We have 2 more to deploy this summer. And that will allow us to get really good data on most of the ionosphere in Canada and around Canada. I want to thank the NSF for allowing me to be here with their travel grant. We also have a website. It's somewhat bare bones right now. It'll tell you the status of each receiver. There's some documentation, but there's a lot more to come, and eventually we will have free access to all of the data that we are collecting with these receivers. We went really fast, so I have time for questions.
Curious about harmonics from power line oscillations in there?
We do. Yeah, we do. One of our systems, it's not the system image there, but in Prince Rupert, we were about 10 feet from the community college that we were stationed at, right below the power line. So we do see harmonics, But since we're doing calibration, we're able to detect those immediately and just kind of filter them out of the data.
How efficient is, when the signal is coming, so I don't work in DLS that much at all. And so, I was just wondering is, how much of a loss in signal intensity do you get under different circumstances?
So, I'm co-author, I'll take this. So generally, for VLF signals in the Earth atmosphere waveguide, we will see 2 dB attenuation over a megameter. So that's the sort of spatial scale of variation that we see. In any particular site, you could see larger or smaller variations depending on the specifics of the waveguide.